Welcome back, everyone. So last time we did all the foundational work. We figured out the motion program for our follower. Basically, we wrote the script for what we want our machine to do. Today, we get to the fun part. We're going to take that script and turn it into a real physical object. We're going to design the cam profile.
Here's what's on tap. First, we'll talk about going from that plan to an actual part. Then I'll introduce you to a really clever trick called the inversion principle that makes this whole process way easier. After that, we'll walk through step by step how to actually draw the cam profile. And finally, and this is maybe the most important part for you as engineers, we'll talk about how to look at our design and ask, is this thing actually any good?
Okay, let's jump right in. So, just to recap, we've already done the hard part of synthesizing the follower motion program. You can think of that as the recipe. We figured out all the ingredients and all the steps for the perfect motion.
And this displacement diagram is that recipe. It is our playbook. For every single degree of the cam's rotation, this graph tells the follower exactly where it needs to be. It maps out the rise, the dwells where it holds still, and the return. On paper, it's a perfect plan. But here's the million-dollar question, right? A graph isn't a piece of steel. A diagram can't push anything. So how do we actually translate this one-dimensional line on a page into a two-dimensional physical cam profile that can be manufactured and put into a machine?
Well, to do this with a graphical approach, we use a fantastic little mental shortcut. It's a key idea in kinematics called kinematic inversion. And honestly, it turns a really complex problem into something surprisingly simple.
Think about it. Trying to draw a weird, lumpy shape that's spinning while also tracking the up and down motion it creates, that sounds like a headache. So with kinematic inversion, we just flip the whole problem on its head. We pretend the cam is bolted to the table, and instead we imagine the follower is the one moving around it. So in the real world, the cam spins and the follower goes up and down. Simple enough. But for drawing it, we pretend the cam is stationary, and the entire path of the follower actually swings around the cam. What this does is it turns a tricky dynamics problem into a much, much simpler static geometry problem. It's a game changer for visualization.
All right, enough theory. Let's get to the drawing board and see how this inversion principle actually helps us build the cam profile. We're literally going to construct the shape piece by piece using our diagram.
It all boils down to a really logical 5-step process. And what's cool about this is that you'll see how you can go directly from the numbers and lines on your motion graph to a physical, functional shape. It's pretty satisfying. So first things first, you draw the base circle. This is the smallest radius the cam profile will have. Then you mark out your angular stations around it, kind of like slicing up a pizza, maybe in 10 or 20 degree increments. These angles match the angles on our displacement diagram, creating our coordinate system. Now, for each one of those angular pizza slices, we go back to our displacement graph. Let's say at 30 degrees, the graph tells us the follower has a lift of, 15 millimeters. You go to your 30-degree line on your drawing, and you measure 15 millimeters straight out from the base circle. You just repeat that for every station all the way around. Okay, this next step is absolutely critical, so listen up. We are not just making a dot-to-dot puzzle here. At the end of each of those displacement lines you just drew, you have to draw the actual shape of the follower. So if you have a roller follower, you draw a little circle. If you have a flat-faced follower, you draw a straight line. You're drawing the part that makes contact.
And now for the big reveal. For step 5, you simply draw one continuous, smooth curve that just kisses the outer edge of every single one of those follower shapes you drew. That beautiful flowing line that is tangent to all those circles or lines, that is your cam profile. You've just created it.
So we did it. We have a shape. It looks like a cam. But drawing a pretty curve isn't engineering, is it? We have to stop and ask the real engineering question. Will this thing actually work? Is it a good design, or is it going to fail spectacularly?
And to answer that, we have to evaluate it against some key criteria. Practical stuff. Is the cam so huge it won't even fit in the housing? How's the pressure angle? Is it going to waste a ton of energy? Are the contact stresses so high that it's going to wear out in 5 minutes? And what happens when we spin it up to high speed? Is it going to shake the whole machine apart?
Let's zoom in on one of the biggest ones, the pressure angle. Imagine you're pushing a heavy box. If you get right behind it and push straight, all your energy goes into moving the box. That's a good low pressure angle. But what if you try to push it from way off to the side? The box just wants to spin and scrape against the floor. That's a high pressure angle. It's inefficient, it creates friction and wear, and it can even cause the follower to jam in its track. As a rule of thumb, we really want to keep that angle below 30 or 35 degrees.
Now let's talk about some absolute deal breakers, the kind of flaws that mean your design is fundamentally broken before you even try to make it.
This is something called a cusp, or undercutting. Think of it like trying to drive a bus around a super tight corner in a parking garage. The bus just can't make that sharp of a turn. It's the same idea here. If the cam profile has a curve that's tighter than the radius of the roller follower, the follower physically cannot follow that path. It'll get to that sharp point, lose contact, and then slam back down. It's a catastrophic failure waiting to happen. And this gets to the heart of why cam design is so challenging. These systems are made of incredibly rigid parts, hardened steel, unhardened steel. This means that even a tiny microscopic variation on the cam's surface, a bump you can't even see or feel, can act like a sledgehammer blow to the follower at high speed.
This is exactly why modern cam design requires insane levels of precision. We're often talking about needing accuracy to 4 decimal places. And let's be real, you are never ever going to get that with a pencil and a compass. The width of your pencil line is bigger than the entire tolerance you're allowed. And this really highlights the main limitation of the graphical method. So, you might be thinking, Professor, why did we just spend all this time learning a method that isn't precise enough for the real world? And that's a great question. The answer is that this method is all about building your engineering intuition. It lets you see the connection between the motion graph and the physical shape. You have to understand how a cam is born before you can properly use software to design one.
Which, of course, leaves us with one big, hanging question. We know how to get the basic shape now, but how do we get the hyper-precise numbers, the coordinates down to the 4th decimal place that a modern CNC machine needs to actually cut the part? Well, for that, we have to put away the drawing tools and break out the math. And that is exactly what we're going to dive into in our next lecture, the analytical approach. I'll see you all then.